so that, okay, welcome everybody. And this is the first lesson, the first actual lesson of the course. And this is about computational and algorithmic thinking. So today we're going to dive into the main topics of the course, and we are going to understand, let's say, what we are talking about when we talk about computational thinking and algorithmic thinking, why they are connected, these two ways of thinking, and what are the main differences, okay? So computational thinking. So let's see a few definitions of computational thinking. So here we have a definition given in 2014 by Wing, in a paper called titled Computational Thinking Benefits Society. And computational thinking is the thought process involved in formulating a problem and expressing its solutions in such a way that a computer, human or machine, can effectively carry out. So here you see we have some key words. Is a thought, not a tough. It's also a tough process because it's not easy, but it's a thought process. And one of the main things is that it is about formulating a problem. So the problem exists, and what you have to do is to formulate this problem, okay? So be able to express the problem. When you can formulate a problem, you can express also its solution using the same language, okay? And you have to formulate the problem and express the solution in a way such that a computer can carry out the solution, okay? Can execute the solution. And here is curious, human or machine, okay? When we talk about a computer, of course, you think about this, you know, a physical computer, a machine, but also I am a computer. So, you know, there is a book that is called When Computers Were Human, okay? Because computers is a computer is a person who do computations, and everything a computer can do, we can do, but we are just slower, okay? So keep that in mind, that the same instructions that you give a computer are those that you give to a human if a human has to carry out the task, okay? It's just the language that's different, nothing else. And the fact that a computer machine is stupid and the human in some cases is not. So another definition given the same year when computational thinking became a thing, and this is in a paper called Computational Thinking in Elementary and Secondary Teacher Education. So how computational thinking should be present in our education path, okay? And CT, so computational thinking, is the mental activity for abstracting problems and formulating solutions that can be automated. So here we have mental activity, okay, the thought process of before. So here we have a mental activity for abstracting problem, which is the same as expressing a problem, defining a problem, for formulating a solutions, okay? And both problems and solutions especially need to be automated, okay? So here you see the key word. The difference with the previous definition is that here we automate. We want to automate the solution, okay? And then, well, if you can activate the webcam, this is really good because I really like to see your faces. It's like I'm talking to someone. That helps a lot. Thank you, and that's great. If your network is good enough, otherwise don't worry. So here we have another definition, even 2 years before, okay, in 2012. And this is about thinking city in UK schools. So here we have the process of recognizing aspects of computation in the world that surrounds us and applying tools and techniques from computer science to understand and reason about both natural and artificial systems and processes. So here we have recognizing aspects of computation, okay? So we are in the real world, and what we need to do is to recognize aspects of computation, okay? And we apply tools and techniques from computer science, okay? So when we talk about computational thinking, we can't untangle computational thinking from computer science, okay? Because computer science is the science behind computers and automation and computation. So you may have computational thinking without computer science if you don't want to automate anything, if you don't want to use a machine. That can be done. Otherwise, we need computer science to understand and reason about both natural and artificial systems. So this was a brief introduction about computational thinking, okay? And we have seen the keywords behind this discipline, okay? Automation, problems, solutions, and thinking, mental activity, okay? So let's see what we talk about when we talk about algorithmics, okay? So sometimes we say that solutions are algorithms. Is that true? Because all of these are solutions, right? 42, which is the answer for everything, right? If you have read the Hitchhiker Guide to the Universe or to the Galaxy, I never remember the right title. So if you read that wonderful sci-fi book, you know that what 42 is. True? Yeah, it's a solution. It's an answer. 1024, 365, for instance, this is a solution for the question, the number of days in a year. That is not always true, by the way. But these are not algorithms, right? So maybe algorithms are solutions. So the other way around. So let's see. Algorithms are sequences of basic steps a non-intelligent being can blindly follow to solve a problem. This is a good definition for an algorithm. What are the keywords here? Sequences of basic steps. So here we are talking about basic steps, simple steps, like something like go to the hardware store is not a basic step. It's a complex step because you have to go to know what's a store, you have to know the route. That's a very complex step. A basic step is 2 + 2, okay? That's a basic step. And an algorithm is a sequence of the most simple step you can think about. Why they need to be basic? Because they must actually be followed blindly by a non-intelligent being. So you take a dumb person, the dumbest person you can think about, okay, that just execute things, but this person cannot reason about things, okay? No initiative, nothing. This person must be able to execute an algorithm because this person is the computer we have. Computers are non-intelligent beings, okay? We will see that, you know, we might talk about intelligence, artificial intelligence, machine intelligence, it's everywhere now. But basically, a computer is as intelligent as the person who programmed it, okay? Well, maybe now going on with techniques, this is not always true, but let's say that for what it is concerned with us, we are talking about sequences of basic steps that a computer can blindly follow to solve a problem. Then the correctness of the solution is another problem, okay? So we have the idea now of computational thinking, this mental process that allows you to define a problem and to think about a solution, okay? And then we have the idea of an algorithm, which is the actionable item you use to actually solve the problem once you know the solution, okay? You know the solution of a problem and you are able to define that. The algorithm is the operational part where you write down, you define the steps, the basic steps to carry out the solution, okay? In a blindly way. So let's see how we can use algorithmic thinking for saving lives, okay? So this is kind of a up-to-date thing, okay? So you might say, okay, for saving lives, I need to be a medical doctor. Well, yes, but not only, okay? And let's see how algorithmic thinking may help in a variety of situations in real life. Okay, so here we talk about kind of a sad thing, which is the locked-in syndrome. I don't know if you ever heard about that. Basically, the locked-in syndrome is a syndrome where you, for any reason, a stroke or whatever else, well, not you, somebody wakes up basically paralyzed. Any function is suspended, but you can think, okay? You can think, you are mentally normal, like the day before, but your body is completely shut down, okay? This happens, unfortunately, and this is called the locked-in syndrome, because you are locked in your body, okay, that you can't move, but you can think, okay? So this is a real story, actually, and this guy called Mr. QWERTY is paralyzed, okay, except for the blink of an eye. So his mental activity is completely fine, and he can blink just one eye, okay? So this guy wants to write a book to describe his condition and help others, okay, with the same locked-in syndrome. So how do we help Mr. QWERTY to write this book, okay? He can just blink an eye, okay? So if you are Mr. QWERTY doctor, you must come up with a way for him to communicate. And this is needed not only to write a book, it's needed to do whatever, right? To communicate basic needs too. So let's think about this. One solution is to turn blinks into letters, right? So you do one blink, and that's for the letter A. You do two blinks, and that's for letter B. You do three blinks, that's for letter C, and then you go on till you get 26 blinks for letter Z or Z, depends if you are UK or US speakers. Okay, so in this way, we have a solution, right? He can blink an eye. Okay, so you just need to count the blinks. Okay, so what we did is that we came up with a sequence of steps that a helper can follow to guarantee the letters Mr. QWERTY is thinking of are communicated. Okay, so you are a nurse, a doctor, whatever. You look the eye of Mr. QWERTY, you count the blinks. And so this is an algorithm because the steps are basic, right? Very simple steps. They are deterministic. You always know the letter that Mr. QWERTY wants to say, right? And you can execute the algorithm, right? You can carry it out. And it's dumb enough. I mean, you just need a person who is able to count, right? And maybe to write the letter in a paper. Okay. Our algorithm has two components, Mr. QWERTY and the helper, say the doctor, okay? They both need to know that a certain number of blinks corresponds to a precise letter. This is needed, right? You need, as a helper, to know that if you see two blinks, that's the letter B, okay? And also Mr. QWERTY need to know that. So algorithms need to follow a protocol. A protocol is a list of rules that an algorithm needs to follow, okay? Because we need to agree on common rules in order to understand the basic steps that we have to carry out. So up to now, we have seen our first algorithm, our first problem, actually, our first solution that can be carried out by an algorithm accordingly to a protocol that allows us to understand the basic steps. Okay? Are there questions? No, okay. So, let's think about this algorithm. This is for sure an algorithm, but is that a good algorithm? Well, first of all, let's think about that. Our algorithm is slow, right? It's slow and needs extra chars. Letters are not enough. We need numbers, for instance. How does Mr. QWERTY express numbers? We didn't think about that. We need question marks. Well, not fundamental, but useful. We need commas, not fundamental, but useful. If Mr. QWERTY is not American, but Italian, he needs letters with accents and so on. And is error prone. It's really easy to get it wrong, right? He's blinking an eye. He may have a mosquito, so he's blinking, but he's not saying anything. He might get dry, and so he does like this, and this is not good, you know? You may mess up all the counting. Think about you are going down to Z, okay? 26 blinks in between the first and the last blink. Anything may happen, okay? You may blink very fast, and so on. So what we need to do is to evaluate our algorithm. And when we say an algorithm is slow, it means that we are evaluating the performances of the algorithm, okay? Performances, efficiency. Is it slow or is it fast? You may have two perfectly correct algorithms, okay, solving the same problem, but one is fast, one is slow, okay? Then, needs extra chars. This means that we didn't actually solve the problem. We just proposed a partial solution, not a complete solution. So our mission is not complete. And error prone, okay? We must ensure that our algorithm is solid to exceptions. Exceptions are always there, okay? Is this algorithm solid enough? Okay, so effectiveness, efficiency, effectiveness, completeness, and correctness, okay? So now we added another layer, okay? We have the problem, we have the solution, we have the algorithm, and now we have evaluation, okay? To understand if our solution is correct and the algorithm implementing it, realizing it, is fast, correct, and complete. So, something that you might think about, and here computational thinking starts to kick in, okay? Starts to come in. Often, the problems you have are essentially the same as something you have seen in a different situation. Okay, so what you might think is, oh, well, wait, is this problem completely new? Or have I ever seen this problem before? And maybe I also applied a solution, or I have seen a solution for the same problem. What you do is pattern matching. So you recognize a pattern, okay, and you match. You say, well, wait. Here I have a problem of understanding letters, okay? Or actually understanding the word, starting from some letters, okay? Where did I see that? Well, we have seen that in predictive texting, like the one you use in your phone. For instance, well, it depends if you are using that predictive texting. Now there are different solutions, but think about that, maybe with older phones. When you write A, M, T, E, L, maybe you have never written this word, but then the phone is suggesting antelope, okay? Because if you write until, probably there are no other words or very little. And maybe you used antelope before, right? So you have a suggestion. So we may use this in our algorithm, right? If Mr. QWERTY starts with an A, with an N, with an T, with an E, with an L, we might say, well, are you saying antelope? So we may have also a sign for saying yes or no, okay? And in that case, we saved 3 words, okay? 3 letters, sorry. So this is pattern matching, okay? This is a pillar of computational thinking, which is recognizing that our problem is similar to another problem for which we have a solution. And another thing is generalization, okay? Because we might have a solution that works for a variety of similar problems, and we can apply it to the current problem. For instance, wow, we have Morse codes, right? Why are not we using Morse code for QWERTY situation, okay? A telegraph is dot, line, we can do that with our eye, right? So we can use Morse code. This is called generalization. So if we apply pattern matching and generalization, these 2 techniques, super powerful, to our current problem, we came up with another solution. And this is that we realize that in written and spoken language, let's stick to English right now, some letters are more common than others, right? Letter A, letter E is more common than letter Z, almost in every language, in Western countries at least. So what we can do is to order the letters on a frequency basis. Yes, right? If we analyze, for instance, all the Shakespeare writings, okay, that's usually what is done for English, we count the number of times letter E appears, letter T appears, and so on and so forth. We realize that the letter E is by far the most frequent letter in English, followed by letter T, A, O, I, N, S, and so on and so forth. So if we use the alphabetical order, to say the letter E, we need 5 blinks, right? But that's the most frequent one. So let's associate the most frequent one with 1 blink, and the least frequent with 26, which in this case is the same, is the letter Z, which is kind of uncommon, okay? So in this way, we didn't solve some problems like completeness of our algorithm, but we speed up the algorithm quite a lot, right? Now the algorithm is faster. Do you agree? Yeah. Okay, so here, as you see, we generalize the problem and we applied pattern matching. So let's think about how fast is this algorithm. So how do we know how fast this algorithm is? And this is another key of this course, analyzing the performances of algorithm, understanding if we can say that an algorithm is efficient or not. So one way to measure that is run the algorithm several times by employing several different people, as Mr. QWERTY and the helper, and measure time. Why we need to do that? Well, we need to have different people because we need to average amongst people who blink faster, for instance, who are more clever, and so on. Sorry, it's very important. I don't know what it is. Okay. So we run it many times so that we take the average, right? This takes time and effort because we need to run the algorithm many times. And it takes time and it's boring, right? And it's also not very precise. So what we can do without employing many people is to estimate the time each letter takes, okay? So let's say that letter E takes half a second, right? Just one blink. Letter Z, 26 blinks, might take 10 seconds, 12 seconds. We estimate that, okay? And then we multiply this time by the number of letters said, okay? Say that we want to say hello, we have H, E, L, L, O, right? So H might take 1 second, say, is 1 times 1. E takes half second, so it's 1 second and a half. Double L, say 2 seconds for L is 2 seconds times 2, 4 seconds, 5 seconds and a half. Letter O takes 3 seconds. Okay, we are around 8 seconds as well. Okay? This makes sense. We don't need to run the algorithm many times. We don't need to run the algorithm at all. Okay? And we already know if it is fast or not, and we can measure it. Here, we used abstraction because we used the number of letters said in place of the actual time taken to say them. Okay, this is abstraction because we are not doing that in the real world concretely. We abstract it and we say, okay, we don't need to say the words. We don't need to actually blink. Well, actually, maybe we just need to count the first time in order to have a correct estimation of the time. But you do that once in your life, maybe once in the world. Okay? We are here today, we take 10 people, we say, okay, let's count the blinks for all the letters. We take the average for each letter. We share this knowledge with the world, and that's done. Okay? Everybody can measure their own algorithm on this basis. Okay? And this is abstraction. And this is another pillar of computational thinking. So for now, we are seeing solutions, problems, solutions, algorithms, evaluation, and then the pillars of computational thinking: generalization, pattern matching, and now abstraction, right? So as you see, just reasoning about this very concrete problem, we are digging into the mysteries of computational thinking. Now, as I told you, how do we estimate how many letters we have to be said, right? Because if we want to be general and abstract, it's not that every time we have to say something, we do our calculations because we want to say, in general, this algorithm is like this. So we have to estimate how many letters have to be said. And what computer scientists do is that they consider always the worst case. Why the worst case? Because when you have an evaluation, an estimation for the worst case, you know that you can always do better than that. So if you say this algorithm is taking, this is not for real or meaningful, but 10 seconds in the worst case, you know that in real life, you are never taking more than 10 seconds. And in most cases, probably you are not even close to 10 seconds. You are 1, 2 seconds, okay? So the worst case can be abstracted because you can think without actually doing that what's the worst possible case ever? And what's the worst sequence of letter we can encounter? Okay, what's the worst? Well, the worst is all Z. That's not even real. But you can't have anything worse than all Z. So when you estimate the execution time of your algorithm for all Z, you know that you can always do better, okay? And you are guaranteed that you cannot do worse than that. And that's super important. Say that you have to save a life, okay? And they ask you, well, we need an algorithm, okay, for this, for solving this problem. But we have a limited amount of time because this guy is dying, okay? So, or in a general situation, the guy must be dying, maybe that might be dying, okay? So you come up with an algorithm. This solves the problem, okay? You can cure this guy with this algorithm. Fantastic, okay? How much time does it take? I don't know. Well, this is not good because if I solve a problem but I do not know how much time that it takes, it's useless. So you go for the worst case and you say, well, in the worst case, say we are in a mountain without network, this guy is really bad injured and so on and so forth. This algorithm works in 2 hours, okay? So the other might say, okay, 2 hours. This means that in all other situations, it might take less. So if you are in a hospital, you have to cure this guy with your algorithm. You say, okay, I know, for instance, I have 3 hours. You know that you can use that algorithm because in the worst case, it is going to take 2 hours. That's fine. Then it might take 1 hour or half an hour, even better, okay? This is the idea of worst case estimation. So when you think as a computer scientist, what you need to do is to think in a pessimistic way, okay? That's the law of Murphy. Do you know the Murphy law? If anything can go wrong, it will go wrong, okay? This is not a good way to live your life, okay? I really hope that you can be a bit more optimistic than this, but when you are providing solutions to problems, when you are writing algorithms, you have to think about anything that might go wrong, and you have to be pessimistic. You always go for the worst case, okay? That's what you do. And when you have a good solution for the worst case, you know that you have even a better solution for the average case, okay? But the average case requires real life experience. You need to know what is going on in real life to come up with the average case. So you can't do the average case in theory. Well, it's hard. For instance, here we can do that and roughly estimate the average case. Because for each A, we might say that there is a Z, and for each B, there is a Y, and so on, okay? So we balance. In this case, we consider the alphabetical order, okay? So otherwise, we might say for each E, there is a Z, for each T, there is, don't remember what it was. So for each E, there is a Z, for each T, there is a Q, for each A, there is a J, for each O, there is an X, and so on, okay? If you do that, the estimate basically is the same. You go up to 13 blinks per letter. That's the average case, okay? If you sum up the worst case and the best case, basically, you get this. 13 blinks, okay. If we multiply by the number of letters Mr. Qwerty wants to say, we have an estimate of the running time, okay? An estimate, okay? So if he wants to write a book, well, we are still in trouble, okay? Because if we have 1 million letters in our book, we are talking about 13 million blinks. But at least we know, okay? We have an estimate. So even though we consider the frequency analysis improvement that we have discussed, this algorithm is pretty slow, right? It's pretty slow. So we may go down to 10 blinks per letter on average, but worst case is still 26 blinks. So, you know, if we improve our algorithm with improvements we discussed, our worst case does not change. And this is something that is very bad for computer scientists, because you say, well, I have a better solution, I know that, okay? You write the algorithm, and then you bring it to me, and they say, well, worst case is the same, who cares? Which is not actually true, because if the average case is better, you might say, okay, this is not a great solution, but it's better, let's use it, okay? But what you really care about is to improve the worst case situation. That's what we aim for, okay? So here, we added another thing to our toolbox, which is worst case analysis, okay? So let's go back. Defining solutions, defining problems, finding solutions, writing algorithm to execute them, pattern matching, generalization, abstraction, evaluation, yes, and worst case analysis, okay? All things that you use in your real life, okay? Maybe you don't know you're using that, but you're using worst case analysis all the time, okay? Say that you have to go to give an exam at the university, okay? You are at your home, you say, okay, the exam starts at 10, right? Okay, I need to be there at least 5 minutes before 10, okay? So how much time does it take from home to the university? Well, if I ride my bike or my car, if I use my car at midnight, okay, the other day at midnight it took 20 minutes. Yeah, of course, no traffic, no people around the streets. I could go with my car in the city center because there were no limitations. Yeah, that's the best case, right? Average case, well, in the last 20 times I went from home to the university, it took like 20 minutes, 30 minutes, 35 minutes, and so on and so forth. Okay, then you took the average, it's 15 minutes. Okay, do you exit your house at 20 to 10 to be there at 5 to 10? I don't think so. It's too risky. You go for the worst case. That might be, in my experience, once it took 50 minutes, okay? So if you want to be safe, you just exit your house 50 minutes before, maybe 45, because that's peculiar worst case also involved, I don't know, heavy rain, and today there is no rain, so you may take out 5 minutes, okay? That's worst thinking, worst case analysis, okay? Sorry. So what you need to do is to think of a better algorithm, okay? To do that, let's play a game. I didn't adapt the game for this audience. I really hope you like soccer, or at least you know a bit about soccer, but otherwise, don't worry. So let's play 20 questions. Do you know what's 20 questions? 20 questions is that you can ask another person 20 questions, and the other person can answer yes or no, okay? And you have to guess who is the person the other person is thinking about, just asking, or the thing, whatever, asking 20 questions. Less questions you ask, the better, you know? If you can guess the right person the other person is thinking about in one question, okay, you are a champion. If it takes 20 questions, you won the game, but it's not good. And then you keep playing. And the one that is guessing right with the least number of questions win the game, okay? Very simple. So there was also a game in the 80s called Indovina Chi, Guess Who in English, and maybe you played that. I don't know. So the first question I'm asking is, are you a female? And the answer is no. Okay. The other question is, are you alive? Question is yes. Okay, so we are talking about a male who is alive. Okay. Are you a film star? No. Okay, we are excluding all film stars. Okay. Are you Italian? Yes. Okay. An Italian male alive. Can be me. For now. Let's go on. Are you a soccer player? Yes. Oh, okay. We are restricting it, right? A male, Italian, alive now, who is a soccer player. So now we are thinking about soccer players in activity and all the soccer players not in activity but still alive. So the next question is, are you still playing? No. Okay. So we exclude all the players, the current players. Okay. So it might be Gianni Rivera for what we know. It might be Roberto Baggio. Okay. Because they are male, alive, Italian soccer players not playing right now. Oh, this is a nice question. Did you win the World Cup? Yes. So we are talking about the team that in 2006 and also 1982, because they are still alive, won the World Cup. So the next question could be, which year? You know, did you win in 2006? Yes or no? But we can also ask, did you play for a non-Italian team? Yes. It's not the best question we could ask, but oh yeah, so you played in Italy, I guess, but also for a non-Italian team. So next question is, are you Andrea Pirlo? I just wanted to cut it short. Yes, I'm Andrea Pirlo. Okay, so with 3, 6, 9 questions, we got the right solution, right? So if we change and we say that one blink is yes and no blink is no, okay, maybe we can play 20 questions with our friend Mr. Purdy, right? And here you see that we are going down to another basic brick of computer science, which is binary language, binary thinking. Yes, no, 1, 0, okay? That's key, that's key, okay? So, but keep that there. Okay, so if we substitute yes and no with blink, no blink, we can always find the right letter with at most 5 questions, okay? This is guaranteed. And here comes in mathematics, okay? Mathematics. You say, okay, if we guess the letter you want to say, okay? Okay, and if we do this guessing in a very clever way, we can do that in the worst case with 5 questions. So in the worst case with 5 blinks or no blinks, okay? Wow, this is much better than the average of 10 that we had in the best case, with the best algorithm before, right? To prove this, you need math. But let's see how it works. Because if you ask, are you thinking about letter A? Yes, no. If it is a yes, best case. In the worst case, what's the worst case for this algorithm? Well, you ask 26 questions, right? 1 per letter, because the letter Mr. Purdy is thinking about is the last one of the alphabet, right? That is not good. So which questions do you need to ask to cut down the problem to 5 questions in the worst case? Start from here. Is it a vowel? Yes, no. If the answer is yes, we narrow down the problem to 5 letters. Else, we're still in trouble, right? Because no, it's not a vowel. Then we have 21 letters to guess. Still better than starting right off asking, is this letter, is this letter, is this letter? What is a better solution? A better solution is what we call binary search applied to binary tree. Okay, don't write it down. This is something that we will learn probably the last week of lesson or something like that, because we're talking data structures now. But it works in this way. If we ask the first question, which is the letter you are thinking about comprised between A and N? If the answer is yes, then we know that we are in between A and N. Okay, so our next question is it between A and F? If it is no, we ask, is it between N and S? So the next letter. So you see what we are doing here. We are cutting the alphabet in half, right? A-N. If is yes, you know that Mr. Curti is thinking about one letter in the first part of the alphabet. So if it is yes, we cut the first half in another half. So from A to F. So if the answer is yes, we know that we are in the range AF. So we cut in half again. And we say, is it AC? Or if it is not between A and F, then we move next. Okay, what is G and J? Okay, and the same goes the other round. Okay, you keep cutting in half. And if you go on, you know, yes, AC, okay, is it in AB? And then, sorry, here, the key 5 is about here. You see that with 5 questions, in the worst case, because it can also be 4 questions, so in the best case is 4, in the worst case is 5, you get to ask, is it letter A? The answer is yes, you are done. The answer is no. You know that the only possible answer is B. Because when you ask, is it in AB, Mr. Curtis said yes. So you know that the letter is either A or B. And this is true, you see, in every case. You always go down with 4 questions to a binary choice in the worst case. In the worst case. Okay? That's great. I mean, with this way of reasoning, okay, so with this algorithm, you moved from 13 letters, 13 blinks on average case, but 26 in the worst case, to 5 blinks in the worst case scenario, guaranteed, okay? You can't do worse than this. So here, I think, you realize the full power of computational thinking, okay? Of course, it's not easy. This solution does not come up in 2 seconds, in 2 minutes. You need to think about that. You need to write it down. You need to look at that. But once you know that this way of thinking exists, you can always try pattern matching and say, well, when I have to guess a letter, I have an ordered sequence, which is the alphabet, right? When you have an ordered sequence and you have to guess something, you know that you can apply this algorithm here. And this algorithm here is called binary search. It's a very well-known algorithm. But if you ask me, I come up with a solution in a few seconds, minutes maybe, if I'm not asleep enough. But I can, why? Because it's 20 years that I know about binary search. I used it in many cases. So when you tell me you have to find something within an ordered sequence, I say, hey, binary search, there is nothing better. And this is another thing that only mathematics can guarantee us. We are not going to see this mathematically speaking. I'm just telling you that this is not only beautiful and fast because of this worst case. This is the best possible solution existing, okay? You cannot find anything better than this, okay? And what we will learn is that the running time, the worst case running time to execute this algorithm is logarithmic. I mean, whatever is the length of what you have to do is logarithmic in the alphabet, okay? So this takes log of 26, okay? We will discuss this. I'm just showing you concepts, just to. So if you need to go for Chinese, that is much more complex than, I guess, I don't know it, but they have many symbols. So say that you order them and you want to guess, right? There are many more. You know that with this algorithm, you can do it in logarithmic time, even though your their n, which is the total number of letters, maybe it's not 26, is, I don't know. It might be 2000. Okay, no problem. It's still logarithmic. Okay? And logarithmic is a great function for engineers. That's the reason why we use it everywhere. Okay, so let's stop for a bit. Are you following? Are there questions? No, okay. So let's move another step above. We can have codes for letters, so we don't even ask. We don't even ask the 5 questions, right? It's boring. Think about the helper. They're asking, is it between A and N? No, okay. Is it between A and F? No, okay. Boring, okay. Mr. QWERTY, unluckily Mr. QWERTY has the locked-in syndrome. So to him, that's great. He gets to speak to people, he gets to express himself, that's fine, we are happy for him. But if you are the helper, you don't want to spend 8 hours a day talking to Mr. QWERTY and just saying, is it between A and M, is it between N and S, and so on. It's boring, okay? And not effective. Why? Because it takes time for you to say AM and say, okay, you can print a table and indicate. Okay, so you don't speak, you just indicate the interval, better. But something even better is to use codes. So you know that 1 is blinking, 0 is no blinking. For blink, no blink is problematic because what is no blink? Okay, but let's do not consider this problem for now, okay? Let's abstract a bit. So you see 1 blink is a 1. So if you are Mr. QWERTY and you want to say the letter A, you say 1, 1, 1, 1, 1 is 1, 2, 3, 4, 5, of course, blinks. So if you blink 5 times, you are saying letter A. Best case, you don't blink at all, you are saying letter Z. Very fast, right? Very fast and without questions. This is called codes for letter. And in computer science, we use it all the time. Why? Because this is the best way to store letters, chars. You do not, you have to use binary chars to store something inside a computer. And you don't want to use hundreds of bits. You want to use as few as possible, right? So this is one of the best ways. You want to store an A, you store 5 ones. You want to store a Z, you store 5 zeros. But in the worst case, in the worst case, you store 5 bits. Great, great. So in this way, you see, if I showed you this table at the beginning of this lesson, I might have lost you right away. Like, okay, boring. Bits, binary language, letter, a table. Okay, learn this. Boring. But with our way of thinking, with computational thinking, starting from the problem, looking for many solutions, I hope that now you can really appreciate these 2 tables. Because these 2 tables summarize all this knowledge that we just discussed, all this thinking about a problem and solution. And with these tables, Mr. QWERTY just needs to learn 26 codes, okay? It's very similar to Morse code, of course, but a bit more efficient. This is not the best solution. Why? Because letter E requires 3 blinks. And what we want is for letter E to require no blinks because it's the most frequent. So we can still improve that. So wrapping up the discussion here, the naive solution is, with a 20 question, is to ask, is it A? Yes, no. Is it B? Yes, no. The clever solution is to ask, is it AM? Yes, okay. Is it AF? Yes. Is it AC? Yes, and so on. This is called the divide and conquer solution. Dividi et impera. Okay? We didn't invent that, we computer scientists. Who invented that? The Romans. Okay? The Romans. The empire, the Roman Empire, applied that all the time for conquering the foreign lands. Divide and conquer. It's much better to take one enemy at a time rather than taking all of them together. Okay? Even better if you put one against the other, okay? And then you conquer both, right? This is called divide and conquer, dividi et impera. And this is one of the most powerful algorithmic paradigm in computer science. And you see that without knowing them, we just learned about the first algorithmic paradigm in our life, in your life, I guess. The thing is that you are not able now, I think, to use it. But now you may be able to understand it and to recognize it when you see it applied, right? Because you see it, you say, okay, you are cutting in half the problem. Divide and conquer is not only cutting in half, you may cut in thirds, in 4 parts, and then you take one at a time. Divide and conquer is called a recursive solution, recursive, because you have one solution, which is in this case asking a question, and you are applying this solution many times over. Always the same, always the same. You are never changing what you are applying. You are changing the object where you are applying the solution, okay? You have a hammer, okay, you can use a hammer with a nail this big, with a nail this big. You can use a hammer also with I don't know, with this piece of iron. Don't ask me why I have this in my desk. Okay, and so you can use it. The hammer is your solution, okay? And the fact that it's recursive is that you can always apply that, the same movement, the same thing, but you change the object, okay? So this is recursion. And when you do divide and conquer, you apply recursion many times over. Where? To a problem that is always smaller, smaller and smaller and smaller, until it gets naive. Is it A? Yes, no. There is nothing simpler than that, right? But to reach that point, you need to keep cutting your problem, narrowing it down. And then you get the solution. In many cases, divide and conquer works this way. You never apply the solution. You have the whole problem, you cut, you cut, you cut, you cut, you cut, you cut. You reach the minimum, the atom, you cannot cut it anymore. You solve it. And when you reach here, it means that you have many little problems. You solve, you solve, you solve, you solve, you solve, you solve, you solve. You have many little solutions. And then you conquer. You put them together in a bigger solution until you get the solution for the big problem. This is another way of seeing the problem of eating an elephant. Have you ever discussed this, for instance, in project management? In project management, they say you have to execute a project, okay? Building a bridge. writing a master thesis, okay? The problem is big, okay? And in project management, they say, well, you know, the problem is far away that you have to solve. So, and your problem is an elephant. But when the elephant is far away, it's that big. So you wait, you wait, you wait, you wait, you don't do nothing. Then you reach the deadline, and the problem is kind of big. It's an elephant. You can't eat the elephant all in one piece. It's too much. But what if you cut your elephant in little pieces and you eat one piece of the elephant every day or every hour? It depends how much time you have. That's doable. I do not eat elephants. I'm sorry for the vegetarians, but it's the classic example. Okay, so you eat this little tiny piece of elephant every day. You reach the deadline, you eat the last piece, and you're done. Okay, this is divide and conquer, literally speaking, because you actually divide the elephant in little pieces and you eat them. So you are conquering. And when do you have the final solution? The last day, when you eat the last bit. But that's doable. Okay, so as you see, this kind of solution, you can find it applied in every cases. You have in project management, you have it in marketing, you have it in everyday life, okay? Even if you don't know it. Of course, which one is better? I think that now we know it. So actually, this was a real story, and Mr. Corti is called J.D. Bowlby, and he woke up in a hospital bed with the locked-in syndrome. And actually, this is pretty scary because he went to sleep and he just woke up like that. And as far as I know, they didn't realize what happened, but that was it. Unfortunately, he didn't know how to think computationally. So he didn't know about these solutions we just discussed, and not even the doctors, not even the family. Nevertheless, he managed to write a book, and that's why we are telling the story, which is, even though you are not able to think computationally, you can solve your problems. It just takes time, okay? And it depends if you have it or not. Now, let's sum up a bit what we have just seen. So, the pillars of computational thinking. What are these pillars? And this is kind of an outline of what we are going to learn in the first week of the course. There will be a lesson dedicated to each one of these, okay? At least one lesson. The first one is decomposition. We just discussed that. Can be because of divide and conquer or for other paradigms. That's not fundamental. But is you have a big problem, right? Very complex. You have cherries, you have cream, you have ice cream, you have a banana, you have a bowl. Then it's a lot of stuff, right? So what you do is try to decompose the problem into little pieces. Okay, here you have all these items. Then another thing is pattern recognition. You see, all these objects are the same, just the color is different, but they are the same. So say that your problem is you want to eat this stuff. With pattern recognition, you say, well, if I know how to eat one of these, I might apply the same pattern for all the others. Of course, this is a stupid example. But then you have abstraction. Well, you might throw away the bowl and the banana. I do not care. What's really relevant here are the ice cream, the cream, and the cherry. Okay. And then the algorithm. Okay. So here, for instance, this is a control flow in which you decide the steps in which you solve the problem. I really don't know what they want to do with this, but think about this, about the algorithm. Well, I don't know. And anyway, the composition, pattern recognition, abstraction, and algorithm, okay? In the case of Mr. Curti, we have seen each single one of these steps, okay? And so here we have another image just to sum up everything, which is the composition breaking the problem into smaller, more manageable parts. Pattern recognition, recognizing which parts are the same and the various attributes that we can use to define them, okay? Abstraction, filter out the data you need and what you don't need based on the previous attributes that you recognize thanks to pattern recognition. And then you have algorithm design, planning the step-by-step instructions that need to be carried out to achieve the goal. So here, in this image, which is nice, you have to build this airplane with Lego. You have a big pile of Legos, okay? So you break it down, you divide all the pieces. Pattern recognition, you put together the pieces with the same shape and maybe color. Abstraction, you throw away what you don't need and you keep what you need. Design, okay? You don't build an airplane altogether. You need to start from somewhere. So you say, okay, the first step is to build the base, then the wings, then all the other stuff. And then maybe I put also something nice because I like a beautiful plate, right? So this is the way computational thinking works. And what we are going to do in this course is what? Is to apply, to learn, deeply learn these pillars, starting to be able to recognize when and where we can apply each one of them, learn the techniques to apply them, and then put everything together to solve a problem, okay? So learning to thinking computationally is hard because it's thinking, right? I mean, learning to think requires experience, but also method. When you think in everyday life, you know, your parents probably, school, from kindergarten, primary to secondary school, taught you to think in a logical way, right? Now, we're doing the same, but you already know how to think. You need, maybe, to add some structure to your thinking in order to introduce computation in your way of thinking. And once you have that, we are going to learn to map this way of thinking into machine readable and understandable language, okay? But first of all, you need to be able to explain, say, to me, the solution of a problem, step by step. Once you're able to do that, then it's just a matter to use a different language. In our case, Python, okay? But it's just a translation. It's like you want to speak in English, okay? And you are Italian, you need, you don't start to speak English from scratch if you are, you are 20 or 30 years old, okay? You want to start speaking in English, and you are Italian, or you are French, whatever, Chinese. You start by translating. You start step by step about thinking about the grammar, thinking about the words, thinking about the constructs, and step by step you put everything together. And after a while, you don't even relate back to your previous language. You just think and speak in English. Maybe not perfectly, but you can do that, right? And here is not different. Before writing Python, we need to think what you want to write, otherwise you write bad programs. And that's the difference between a programmer and a computer scientist, okay? A computer scientist thinks and design algorithms, and then he or she is able to implement them. A programmer often just translate and write programs, okay? So if somebody has defined the program at a high level, that's fine. If you have also to find the solution and you are a great programmer, It's not said that your program will work, because you need the thinking before that, okay? And that's what the university is for. Not only here, everywhere. Sometimes, when I taught computer design, web design, they were like, why don't we use word reference or stuff like that? It's fast, it's immediate. Or why don't we learn about Excel or stuff like that? Because you don't need to learn the tool. Of course you need that. But before that, you need to abstract. You need to learn the basics, the way of thinking, the general rules. Why? Because those you can apply everywhere your whole life. You just need to learn a different tool. If you learn the tool, once the tool is old, you are done, okay? Think about that. With computer science is everywhere, but it's there also for marketing, it's there for economics, it's there for many other things, okay? For instance, when I started university, I learned Java, okay? And before that, I learned C++. And before that, I learned C as programming language. Okay? Now, Java, at the time, 20 years ago, everything was written in Java. I was like, okay, I just need to learn the language. But now everybody's using Python. And tomorrow, everybody will be using, I don't know, Scala maybe, or Haskell, or other languages that are coming up like mushrooms, okay? To me, using Java, using Python, using Haskell is the same. Well, it's not the same. I need to learn the syntax. And you will see that with Python every time I do something wrong because I don't remember the syntax by heart because I learned it last year. But it's very fast because I learned the general rules. I learned the way of thinking. I know what a programming language is. I know what computational thinking is. I know what an algorithm is, okay? And you always apply the same pattern to learn a new language. It's what they say. Once you know one foreign language, two foreign languages, then it's much easier to learn another one and another one. Why? Because you have the mechanism to learn the new languages. But the first time you learn one foreign language, that's super hard. Okay? Because you have to learn the basics of learning, okay? I hope that this gives you the idea not only about computational thinking, but this is really the foundation of this course, what this course is about. Give you the basic bricks that you can apply wherever you want afterwards. We are applying them in Python because we need something to apply to, but just a choice, okay? And this is true for the university in general. And that's why university, this is not for computational thinking, but I like to talk. And this is why university is different from a master. It's different from a course you can take on Coursera. It's different from a specialized formation they can give you in a company. Those are all important and very useful once you have the basics that university can give you, okay? That's so important. Now you are at university, I'm talking about university, but it's true for school in general, okay? And I think that being able to think and to learn is what makes the great difference in life between a good professional and a great professional. The great professional is fast, is clever, of course, but she knows how to learn, okay? And when you know how to learn, you can do whatever you want. And here with this course, you will also be able to think in a very smart way. And if you can apply it to everyday life, I guess you will have another competitive advantage towards your colleagues. And of course, it's not always fighting against the others, but sometimes it is. So it's better to be the best when it comes down to it. Or at least one of the good ones, okay? So I hope that this motivated